Welcome back. So this is a lecture on optimal control and could be a long one, so I'll try to break it up into a couple of parts. So first we'll go through what we mean by optimality, primarily from the aspect of what we have to minimize or what kind of constraints we can put in and things like that, and then we will look at what was common in the past and what is now common in modern control and things like that. Then we will actually pose some of the problems in open loop optimal control, the stuff we looked at in terms of calculus of variations or optimization. They are typically useful in open loop optimal control, but then we'll look at those problems first, followed by a very important principle that actually is applicable far beyond control systems and things like that, some dynamic programming principle. At a high level, it's actually a very brilliant observation, but it's quite easy to understand. But how it applies to various problems is what we will look at, specific to controls, of course. We will look at feedback control, both linear and nonlinear cases, right? So with that, we will look at performance measures, right? Now, before I start with specific measures, the standard disclaimer I want to remind you, basically we assume that there are actuators and sensors and things like that. So for example, if we think of James Watt's governor or your good old flush tank, or even iron box where we have a thermostat and that controls the temperature, so to speak. There were ingenious instruments which actually work as sensors and to some extent actuators in one instrument, right? And we're not going to think about performance of that kind, how well the hardware is designed and things like that. Here we the entire purpose of doing this nonlinear control is, the assumption is basically we have a computer, digital computer or an electronics chip that connects basically your sensor output to actuator input, right? So, and then we when we say we want to optimize, it's the performance of the overall system through this feedback control. So we will essentially be talking about how to connect these two, the sensor output to this thing. And in fact, specifically we'll make an assumption for rest of the course is basically we have sensors available for the entire state. So each state can be measured and things like that, and we will take that and then feed it back through our control input, and it's the algorithm that connects these two is what is we are going to criticize, right? So in the classical control sense, where we had good old single input to single output transfer functions, the primary performance measure seems to be in those days is gain in phase margin, and we will look at these two things very carefully in the next lecture or so. The gain margin is something to do with basically this controller might suddenly get some uncertainty that actually multiplies. We think that we are putting 2, but it's actually 3, some 1.5 factor. Does this system still remain stable? Phase is a little bit more complex to understand, but we will look at that carefully at a later point, right? These are the primary performance measures of a controller, but of course, they were also looking at along the same lines. This is gain in phase margins are specifically with respect to the control parameters, but you could actually have unmodeled uncertainties. There could be unmodeled parameters or nonlinearities, as we have seen in the absolute stability problem. So, how much a particular control scheme allows us to stay stable in spite of these unmodeled uncertainties or nonlinearities, right? So that's a good thing to have. So we could measure the performance of a controller in that sense, right? Then came along what we call as time domain specifications, but still for the same classical control where we have this single input or single output transfer function, and all the methods were still in frequency domain, but we could at least solve the problems in time domain. So peak overshoot is a good performance measure in the sense that basically I want to reach 0 or a 10 or a whatever the number, reference number that we want to reach. The state may actually go from 0 to 10, but it goes beyond 10, and how much it overshoots is a good thing to know, right? So ideally speaking, we would want an optimal control that goes directly to 10 without really taking a long time. So again, how much time it takes to reach that the number that we are intending to reach and things like that. And then settling time, suppose if it has oscillations and things like that, how long will it take for it to settle down to the target number, right? All these are quite important, and basically in the time of classical control, they came up with this idea of PID control. Essentially, this U is connected to the sensor states or output specifically through proportional, integral, and derivative control. So you will take the sensor output, either multiplied with some factor or integrate it for a while, and continuously integrating, and then multiply that by factor and take a derivative, right? And it has been shown that for various classes of systems, the PID control is quite good in terms of ensuring that the target value is reached and things like that. Beyond the basic property of stability, then people were looking for gain in phase margins, through absolute stability problem, other robustness, peak overshoot, rise time, settling time. And it's an obvious point that basically settling, so you have so many performance measures, and then we can't optimize all of them. So typically it may not be an optimization problem, but just some problem that says, okay, I'm going to design a control that that satisfies certain specifications, certain constraints with respect to all these things, right? And a lot of these properties or measures are actually directly related to where the poles of the closed loop are placed. So in general, people looked at techniques of what they called as pole placement, and it's not perfect science, but today, for example, in the presence of things like MATLAB and things like that, we can actually do a wonderful job in terms of placing the poles anywhere we want. Actually, we can even go further and minimize any of these specific things and look over 3 or 4 parameters that we have in the controller and search the entire space and look for something that's valid and things like that. But you get the idea that these are all the measures that we were looking for in terms of satisfying in terms of a constraint or minimizing and things like that. So as I said, this works very well for SISO systems because typically they may have PID controller with 3 parameters and things like that. But MIMO and nonlinear systems may require other measures and design techniques. And anyway, classical control was feedback control. There is other side of this coin of feedback control is open loop control. Now I want to pause a little bit and then say, early part of the 20th century is when feedback control was kind of the basic principles were being invented and things like that. And the part of the world, the Lyapunov stability was getting discovered, and then techniques of nonlinear control were slowly getting developed. But then people also discovered the need for solving this open loop control problem, and a classic example I would say is sending a shuttle from Earth to Mars or something like that. Now if you actually think about it, once it is beyond let's say Earth's atmosphere, you only have gravity from various planets and other objects coming into picture, and essentially the assumption is there are no uncertainties. The unfortunate fact is basically you have too much debris now in space, and then therefore that may not be a safe assumption anymore. But even that, all of those objects have very predictable paths and things like that, and therefore hardly any uncertainties. In such cases, one can actually go for an open loop control in the sense that you can actually design the entire path and then implement that without any fear of some uncertainty or disturbance spoiling the entire thing. But of course, even BIM, otherwise, open loop control has been there for a long time, but not optimal open loop control. I mean, so for example, when we switch on a heater when it is very cold, or switch on an AC and things like that, this is a manual intervention. You can treat that as an open loop control simply because there is an automatic no automatic feedback, but it is actually a feedback control. So you can think of open loop control is basically, if I know exact path, if the road is there and then I want to your typical Google Maps these days basically tell you how to go, is one of those open loop control type of things. It will tell you how to go and things like that, but specific speeds and things like that may require actually feedback control. So anyway, so open loop control works very well when there are no uncertainties and things like that. And then feedback control is important. Open loop control is equally important, and depending on the case, you may actually have to use combination of these two. Something for stabilizing something, the other one is more for just controlling, going from one point to another point. Open loop control typically is useful from going from one point to another point, whereas feedback control is more about stabilizing to a particular trajectory or an equilibrium point, and then after that it should hopefully remain there even with a little bit of perturbations. And that's why we focused so much on stability when it comes to feedback. The standard performance measures when it comes to open loop control is can we minimize the time that it takes for us to go from one place to another, right? And then of course the other extreme is basically can I go there with the minimum amount of cost that I can spend on that particular control, right? Maximum utility is another way of looking at open loop control problems. Utility is again one of those cost functions that are abstractly defined. And the techniques that we learn in open loop control quite well equipped to actually handle many different types of constraints. You can have constraints that are put on state. You can put constraints on control. So for example, in the case where we have the minimum time problem, if you don't have constraint on the control, typically we will end up with no solution. I mean, or rather ridiculous solution like put infinite amount of power or something like that. So we need to put some kind of constraint on control magnitude. So you have to formulate these problems in a certain way, but open loop control can actually handle many different type of formulations. And when you actually get away from this very difficult concept of needing stability, we can actually do wonders in terms of solving the control problem, as long as basic controllability assumptions are satisfied, right? Just a quick note on this controllability and things like that. In linear systems, basically, if you can show that this system can be controlled from going from A to B, and that's it. That's enough to show that it can go from any other 2 points C to D and things like that. When it comes to nonlinear systems, that's not the case. From every point, you may actually have only certain reachable space and things like that, and that makes the problem much more challenging. But open loop control does not kind of worry about those things. It tries to solve, and then if there is a solution, well and good, and then that tells you that whether you're trying to reach the point in a space of reachable space and things like that. Anyway, so design is actually very similar to what we have seen in calculus of variations, and we will see that soon enough. And like I said, we cannot hope for any stability or robustness. It's very good where we don't have those uncertainties. But I mean, the obvious statement is there's no feedback, therefore you cannot have any kind of robustness and things like that. The key thing is basically open loop control problems. You can actually really solve these things through numerical methods and things like that, and it's a truly nonlinear technique. As I mean, Lyapunov functions and stability are there, but there's still no general technique in terms of figuring out what the Lyapunov function. Whereas this one has, you can actually try and attempt to solve this particular problem, but it has its own drawbacks. It's very limited to cases where there is uncertainties and things like that. And the last thing I want to talk about performance measures is in feedback control, and typically we assume that we require stability, otherwise feedback is typically unnecessary. And again, the performance measures will involve gain, phase, and disk margins. We'll see what they are. And then peak overshoot and rise time can be considered, but typically when it comes to MIMO systems, basically the meaning of those things will differ a little bit. What do we mean? I mean, when we have so many different outputs or states, what do we mean by peak overshoot and things like that, right? So it should be some norm based peak overshoot and things like that. Now, as we have seen earlier, basically minimum time in minimum fuel or both are say extremes of the same optimal control problem, but instead we could actually put a quadratic cost, right, and solve that, right. So we'll see again what those quadratic costs are, as we progress in the lecture. And then there are these very strange things called H2 norm, H infinity norm, and L1 norm. So H2 norm is essentially typically applicable to again linear systems. It's one of the norms on H2 and well, let me finish the discussion at H2 norm is a specific norm on the MIMO transfer function. And to give an intuitive meaning, basically it is related to impulse response. It's related to response of a system to some kind of white noise disturbance, right? So it measures basically the system response to some kind of white noise in a particular fashion. So we can minimize the H2 norm of the closed loop so that we know that it's robust with respect to white noise, right? Similarly, H infinity norm is also something to do with response to a disturbance of a different kind. The disturbance in fact need not be stochastic in nature. It could be simply bounded in a square sense, right? Integral of u square t is less than infinity is the type of signals that we deal in H infinity norm. It's an induced norm. The output, how much output norm, the square norm is related to input square norm, right? And that somehow ends up being basically the so-called infinity norm of the transfer function. And these are really wonderful topics to study, which we will not have time in this particular class, but something that you have to look at it. L1 norm is actually another very interesting norm, again the same kind of induced norm where the input is assumed to be bounded, output is assumed to be bounded in infinity norm sense, the maximum value, and L1 is the induced norm. And for a long time it has been an open problem, and then eventually they solved for certain special cases, and there's been a lot of work. The L1 norm is probably the most practical norm that one should work with. So these are all different performance measures. We can define similar norms in the nonlinear systems case, but it's not that easy, right? So in that sense, you can treat them as open problems to be solved in nonlinear systems in terms of minimizing any of these norms. Right, the H infinity norm, as we'll see, we will address the extension of that in nonlinear systems to some extent, but not the other ones. So anyway, of course, other aspects, just as in classical control, robustness to modeling errors is equally important. And in the linear case, we can design using the standard robust control techniques that we have seen in frequency domain, but the same thing can be done in state space, as we have seen through dissipativity theory or absolute stability problem. And I don't have to drive this point many times. Nonlinear optimal feedback control remains a very difficult problem, right? So hopefully you understand the type of measures that we will be looking at, and we will pick some specific measures and solve, propose a problem, and then try to solve those things in the next part of this lecture. We'll start looking at this optimal control problem, which is, as I described earlier, it's an open loop control problem. So, as usual, we'll consider a nonlinear dynamical system. For this particular solution, it does not matter whether it's time invariant or varying. So I'm going to assume the more general one, which is time varying. So x dot is equal to f of t, comma, state and a control. right? So and then we'll call this script u as a set of all feasible control functions. The feasibility could be basically, you know, all functions u of t such that the maximum value of u of t, absolute value of u of t, is less than or equal to, I don't know, 1 or something like that, right? Or maybe the square integral of u could be less than 100 or something like that. So those kinds of constraints, or maybe the constraints could be on the derivative, you know, u dot should be bounded and things like that. So whatever the physics demands, or whatever the physical constraints that we have demands, is what we are going to put in u, right? So, and we'll slowly define this cost or performance measure to be minimized. Like I said, you know, we'll consider the minimum minimization problem, but the maximization is exactly the same with a sign difference, right? So we will look at j, but you know, just as a remark, j only depends on u of t, right? Eventually, because that's the only thing that we have control over, right? It actually depends on x0, the initial condition, but we don't have a control over that. So we will have to solve a problem where the initial condition is just a parameter, and then solve the problem there. Now what about x? X is actually dependent on both x0 and u of t. And if you remember the notation, basically s, you know, this flow, which depends on initial condition, the current time, and initial time, right? So so in that sense, x is dependent on u, so j depends on u. But j could be actually an explicit function of x and t and things like that, and then indirectly everything boils down to just u2, right? So, and we will pose that problem in that specific manner, okay?